Welcome to our next lesson segment on decisions under risk. As I've mentioned earlier, when we know all of our probabilities, we're said to be operating under risk. The classic definition of risk is when we either know for certain what the odds of a given outcome will be, or if we could derive those precise odds. Decisions under risk give us complete knowledge about the probabilities that our decision maker is facing. Because we understand the probability of an event occurring, like heads or tails with a coin flip, we can appreciate the risk of making one choice over another. In other words, if I'm approached by someone who asks me to bet $5 on a coin flip for the chance to win $10, I can more clearly appreciate how much of a risk I'm taking to get that desired win. This is because I know my precise odds of winning. I'm not operating merely on my feelings for or against that outcome occurring because I have more mathematical information to work with. We face decisions under risk in many different contexts in our everyday lives. For example, decisions under risk can be found in business decisions, investments, legal negotiations, and even health-related matters. Heart transplants today are a perfect example of decisions under risk. While we may not have known the precise probabilities associated with the success of the first heart transplant in the late 1960s due to the lack of data and information, we now have enough knowledge after repeated trials and surgeries to surmise a probability of survival. A person faced with the decision to undergo the surgery today can know his or her odds of survival and appreciate the risk of undergoing this procedure. While we'll get into some more complex scenarios later, let's start with an easy example of a decision under risk. Let's say I approached you with the offer to choose one of the following. You can choose choice A, where you'd receive a guaranteed $1 million, or choice B, where you would receive a raffle ticket that has a 50% chance of winning $3 million and a 50% chance of winning nothing. Which would you choose? I'll give you a few seconds to think about it before continuing on. I'm sure that many of you have an idea of what option you'd pick. I'm also sure that many of you are undecided. Decision theory in this situation may be able to help lend a helping hand with making the most rational decision. There are a few different methods for finding a rational alternative with a decision under risk. They are the principle of maximizing expected monetary value, the principle of maximizing expected value, and the principle of maximizing expected utility. They all require you to plug in the information that you know about the situation to find a weighted average for each of your choices. While all of these methods have similar equations, there are different meanings associated with each. Most specifically, the difference between the three equations involves the types of things you are measuring when you're evaluating risk. For some decision makers, money, or monetary value, is the most important factor when making a risky decision. For others, some other determined yet non-monetary unit of value can greatly affect whether a decision maker will make a risky decision. Finally, there are others who put a precise value aside and who place personally assigned values or utilities at the forefront of the decision problem. As our materials show, the principle for maximizing expected utility is the most dominant way to assess situations under risk. While we will spend the bulk of our time discussing maximizing expected utility in our next lesson segment, let's first take a few minutes to think about maximizing expected monetary value and maximizing expected value. Let's begin by learning how to represent decisions under risk in a decision matrix before moving on. Regardless of the way our decision maker solves under risk, it's important to visualize the problem at hand. The easiest way is to start by creating a decision matrix so we can see precisely what elements of the decision problem we know and what we don't know. Let's turn back to our question between choice A, the fast million, or choice B, a ticket with a 50% chance at winning $3 million. Believe it or not, We know a lot about our decision problem just by the information we have already. We can start to visualize everything as a decision matrix. We have choice A, a fast million, and choice B, go for broke, on the left-hand side of this matrix as our two alternatives in the decision problem. We can deduce from our scenario that we have two states of nature associated with this problem. After all, there's an equal probability of something beyond the decision maker's control occurring, as scenario B mentioned. In the case of a lottery ticket, the states of nature could be that the lottery chooses your number, or it does not. In the case of a coin flip, the states of nature could be that you're getting heads or you're getting tails. For the sake of keeping things generic, I'll just call our states of nature State 1 and State 2. The most important thing to concern ourselves with here are the probabilities associated with each state. I've labeled State 1 and State 2 with a probability of 0.5 for each. 0.5 is just the numerical representation of 50% or 1/2. It's useful to already have this number converted to a decimal value so that it may be easily plugged into the various equations regarding this decision problem. It's important to mention that the probabilities associated with each state should always add up to 100%. Or, if you're working with decimals, as we are here, they should always add up to 1. Here, State 1's probability is 0.5, and State 2's probability is 0.5, and together they equal 1, or 100%. Another important thing to note is that the probabilities for each state tell us precisely what the probabilities will be for each outcome of that state. So, as we read down the column for State 1, choice A's outcome will be 50%, and choice B's outcome will also be 50%. Now that we have our alternatives and states of nature with corresponding probabilities in order, it's time to fill in our outcomes. You already know a lot about what our outcomes for this problem will be based on the choices I gave you. Let's start with choice B. For choice B, we know that you're dealing with a 50-50 shot of winning $3 million. In the event that the state of the world is favorable to you, like if the lottery pulls your number, your outcome will be $3 million. In the event that the state of the world is unfavorable to you, or if they don't pull your number, you will win $0. These are reflected in the decision matrix for choice B. Regardless of the state of the world, your shot at $1 million is 100% for choice A, so your outcome for both State 1 and State 2 will be $1 million. It doesn't matter if anyone pulls your number for that given lottery, because you know, regardless of a state, you will get $1 million. Now that we have our decision matrix filled in, it's time to start using some of the prescribed calculations for solving this decision under risk. With the values in place, what can we do to make a judgment call on which option is best? One way to think about the problem is through maximizing the expected monetary value. The expected monetary value is the weighted average of probable payoffs for a given scenario. To calculate the expected monetary value, we need to calculate each choice separately by plugging the information from our decision matrix into the equation you see on this slide. Let's use this example to calculate the expected monetary value for both choice A and choice B to determine which choice is the best between choice A and choice B. For each choice, we need to multiply the probability of each state of nature with the corresponding monetary value of each outcome, and then add everything together to find the expected monetary value. After plugging all of the information into this equation, we find that the expected monetary value of choice A is $1 million. For choice B, we see that there's an expected monetary value of $1,500,000. After plugging in all of our variables for choice A and choice B, we have our answers. The expected monetary value for choice A is $1 million, while the expected monetary value for choice B is $1,500,000. Decision theorists who propose that maximizing the expected monetary value would tell us that choice B, which is slightly higher than choice A, is the most rational choice because the expected monetary value of B is greater than that of A. Although the expected monetary value may be greater for B than A, is it truly the better choice? After all, we're putting ourselves in a position where we forego a very large guaranteed amount of money to take a chance at going for broke with a 50-50 shot at $3 million. We'll evaluate how reliable expected monetary value is in just a little bit. But for now, let's take just a few more minutes to explore other ways that we can apply this concept to decision problems. I think it's important to take a couple minutes to talk about why we care about expected monetary value in the first place and what its connection is with decision theory. You might recall in some of our earlier discussions this semester that the origins and alignment of decision theory are deeply based in a lot of different backgrounds, one of which is economics. Expected value, and more specifically expected monetary value, is the byproduct of economic decision theory. It helps us make mathematically sound economic decisions. So, for example, when we have a question about whether to make an investment or to assign a reasonable price for the services that we provide, or prioritize our requirements, or just calculate the return on investment overall, this is where expected monetary value really comes into play and can really help us. We can also apply expected monetary value calculations to simple, everyday occurrences. When we want to know whether to spend money on an extended warranty for our cell phone or different appliances, whether we'd like to buy life insurance, or even if we'd just like to buy a lottery ticket, this is some place where the expected monetary value can really help us. Let's see how we might apply expected monetary value to other games of chance. This time, let's take an example where we'd like to know how many lottery tickets we should buy in a certain scenario. Let's take a different look at expected monetary value and see how it can help us in a different context. Here's an example. This time, let's think of it in terms of investing in a lottery ticket. Let's say that you've decided to participate in a lottery where 300 tickets are going to be sold. You've already decided that you want to definitely buy a ticket, but you need to decide whether you will buy 1 ticket or 3 tickets. Tickets for this particular lottery cost $2 a piece, but if you decide to buy 3 tickets, it will be $5. The payoff overall, if you do have a winning ticket, is $600. What we need to do here is to assume that money is the only relevant payoff. In this instance, a good way to start this problem out would be to map it on a decision matrix to attempt to solve the problem. Remember, what you're trying to solve for is whether to buy 1 or 3 tickets. Let's get started by mapping this out as a decision matrix. I'll give you clues along the way as to how we're going to complete this for the sake of the problem. First, we set up our decision matrix just like the one in front of you. If you notice in my decision matrix, I have 2 options. I can either buy 1 ticket or I can buy 3 tickets. I also have 2 states of nature. My first state of nature would be that I own a winning ticket, and my second would be that I own a losing ticket. Remember, these things are outside of my control. I can't control whether I have a winning ticket. I can only buy a ticket. So what we need to do is determine the outcome for each and every scenario that goes on in this decision problem. Remember, there are going to be 300 tickets that are sold in this particular lottery. The cost is $2 for 1 ticket and $5 for 3 tickets. This is all the information that you need to determine the expected monetary value for each decision alternative. Let's build out our decision table by filling in the outcomes for each alternative and each state of nature. If I buy 1 ticket and it's the winner, I might represent it like this. If you noticed, I subtracted the $2 that I would have spent on the ticket from my overall winnings if I do have a winning ticket. So that's why the answer for this outcome is $598. Also, my probability of winning is 1 out of 300 tickets because that's all I've purchased. On the other hand, if I buy just one ticket, but I end up owning a losing ticket, it might end up looking like this. If you notice, my overall winnings here are -$2 because that's what I would have spent on a losing ticket. Also, my chances of losing are 299 over 300 because I only purchased one ticket. All we need to do from here on out is to fill in the information that we know in the decision problem. Right now, this is what it would look like if I bought 3 tickets and I ended up having a winning one. And finally, here's what my completed decision matrix might look like once I've filled in all of my information. Now, all we need to do is to plug these answers into an expected monetary value calculation and decide which one has the highest value. After plugging all of these variables into my expected monetary value problem with the information from the matrix, I come up with the following values. For buying one ticket, I find that the expected monetary value is $0, while buying 3 tickets is $1. Because my expected monetary value is larger for buying 3 tickets, I should invest in 3 tickets instead of 1. But remember what I'm solving for in this problem. It wasn't a matter of whether I wanted to invest or not to invest in the first place, but rather it was what kind of an investment strategy I would like to employ. That is, am I going to buy 1 ticket or am I going to buy 3 tickets? Here, the expected monetary value calculation helped me choose the best decision strategy, whereas I was less concerned whether the overall investment was sound in the first place. Here are a few additional practice problems to test your knowledge of expected monetary values. After you try to set these up and solve them, go to the next slide and check your answers. How did you do? The next time you're tempted to participate in a game of chance, buy a warranty, or make a calculated monetary risk where the probabilities are known, consider doing an expected monetary value calculation to impress your friends and family. As we went through our last few problems on expected monetary value, I'm sure you questioned the reliability of expected monetary value and its ability to help our decision maker choose rationally under risk. Although a decision maker can calculate the expected monetary value for a general glimpse at the weighted averages for a particular risk, it does not take into account the actual feelings that the decision maker has towards making that choice. There are many different factors that can weigh on a decision maker's feelings towards taking a risk that has less to do about money and more to do about other things. Let's think about this on a personal level. The true value of various alternatives in a decision problem may vary significantly for a decision maker. For example, a person looking to purchase a house on the shores of a tropical island may be willing to pay more than the calculated expected monetary value for that house because the weather, locale, and scenery provide extra value to that decision maker. Likewise, a person who scrimps and saves for years to have a down payment on his dream home today may be less likely to take a risk on a hot tip on the stock market for the chance to make money in the near future. To that person, this risk may not personally be worth as much to him as the calculated estimated monetary value represents. As we'll see in our next lecture on utility, there are more accurate ways in decision theory for decision makers to choose between alternatives. The expected monetary value may be something that greatly influences a decision maker's choice between one alternative over another, but as we've seen from our examples in our materials, money isn't the only factor that may be considered by the decision maker in such a scenario. Another way to think about a decision problem under risk is by calculating the expected value for that problem. Like expected monetary value, the expected value is a weighted average of the probable payoff for each scenario. Instead of a monetary value, the decision maker is more concerned with the value created by the overall decision problem. As our materials state, value can be measured in a number of ways. A notable example from the book is moral value. But just like monetary value, non-monetary value can have an unusual effect on how this type of decision is perceived and measured. It attempts to dictate how a person should or should not make a decision based on general numbers alone. It does not take a look at the issues in a more personalized way that is unique to our decision maker. To accomplish a much more personalized view at a decision problem, we turn to the concept of utility. Decision theorists have found that the accurate evaluation of a decision under risk can be done through maximizing expected utility. Expected utility is solved by using the equation in front of you, with U standing in for the utility associated with each outcome. But what is utility, and where does it come from? Why is expected utility so helpful to solving for problems under risk? In our next lesson, we'll discuss the concept of utility and how maximizing utility plays a pivotal role in decisions under risk. Please continue to our next lesson for more information.